Hey guys, this is a video for 5.3, which is over the definite integral. So in 5.1 and 5.2, we talked about taking antiderivatives, which we also called indefinite integrals. Here we'll be talking about definite integrals, which are similar but a little bit different. So we'll talk about what definite integrals are, talk about something called the fundamental theorem of calculus, which should sound very important. We'll look at the properties of definite integrals. And the last thing, we'll interpret these definite integrals as an accumulation, whatever that is. So what are definite integrals? Let's start with the fundamental theorem of calculus. So if f of x is a continuous function, right? So remember what a continuous function is. So if it's a continuous function on an interval from a to b, and if capital F of x is any antiderivative of f of x, right? So we also use the word integral instead of antiderivative of f of x. Then we say the definite integral of f of x from a to b is, first off, this on the left is what we call the definite integral from a to b of f of x, and that is equal to capital F plug in b minus capital F plug in a. So you take the antiderivative, you get this capital F, then you plug in the top guy and subtract plugging in the bottom guy, and that is the definite integral from a to b of little f of x. This represents the amount accumulated by f of x as x increases from a to b. So all that means is that this is the difference from f of b to f of a, which is exactly what that subtraction means. But we can use this integral to represent an accumulation of capital F of x. Lastly, note that here I said any antiderivative, right? So when we were taking antiderivatives, we found a bunch of them and we just called it capital F of x plus c. And so here, since we're doing the subtraction, you can take any antiderivative you like, and so we'll just take the one where c disappears. So what that means is when we're doing these definite integrals, you do not have to do a plus c, because we can take any one we like, so we'll take the one with c equal to 0. Let's look at an example. So this says, what is the definite integral from 1 to 2 of 2x dx? So notice that it looks very similar to our indefinite integrals from before, except for these two numbers. And those two numbers, 1 and 2, are what tell us that this is a definite integral and not an indefinite integral. So what I want to do now is identify little f of x and capital F of x. Little f of x is the stuff inside my integral, so that's 2x. And capital F of x is the antiderivative of little f of x. So what's the antiderivative of 2x? Well, that is x squared. All right, this step here I won't do for the rest of our examples going forward, but if it helps you, you can write it every time to remember to plug in the correct thing for that antiderivative. So let's plug those things in. So we have the integral from 1 to 2 of 2x dx. So we know by that fundamental theorem of calculus that what we want to, what that is equal to is f of x, where we plug in 2 and then subtract plugging in 1. And I'm going to introduce here this new notation. And what that means, right, so that's f of x, and then this bar means evaluated from 1 to 2. And what that means is plug in the top 2, and then the bottom, whoops, not equals, but subtract f of the bottom. So that's 1. Right, so that notation where you have some function of x and then a big vertical bar, and then you have a number at the bottom and a number at the top, that means plug the number at the top in and then subtract plugging the number at the bottom in. So we use that notation along with these definite integral notation. Right, so now we need what is f of 2, capital F of 2. So we're plugging 2 into here, so we get 2 squared minus 1 squared. So that's 4 minus 1, which is 3. So that is, notice the difference between a definite integral and an indefinite integral. So an indefinite integral, for example, we had this 2x dx guy. The indefinite integral of 2x is x squared plus c, and that's a function of x, right? You input x values and it's going to output a number. If you compare that to a definite integral, our answer from the last example was 3, and that was not a function of x, but a number, right? So the indefinite integrals are going to spit out a function. The definite integrals spit out a number. And I've already alluded to this some in class, but that number is actually an important number. That number represents the area between the graph of this function and the x-axis. But we'll start talking about that next section. All right, what's important now is to notice that the definite integrals do not spit out a function, but should spit out a number. So let's look now at these properties of definite integrals where we use that fundamental theorem of calculus. All right, so we'll start with let capital F prime of x be equal to little f of x. So that's the same as saying that the capital F prime of x is an antiderivative of f of x. And another way to write that is that the antiderivative of f of x dx is capital F of x plus c, right? That's how we would normally do that in the last section. So if you have this scenario, then we can look at all these properties where instead of talking about this indefinite integral, we can talk about definite integrals. So let's start with letting k be any constant, so that's any number you like. Then the integral from a to b, the definite integral from a to b of k times f, is k times the definite integral. So that k can come outside of the integral. And then using our fundamental theorem of calculus, that definite integral is equal to f of b minus f of a. And so what that means is just that we can pull these constants out of these definite integrals and then find them like normal and multiply them by that constant. That should look familiar. That's the same rule we used for indefinite integrals, the same rule we use for taking derivatives, that constant can come out and always just comes along for the ride. All right. The next property is that the integral from a to a, right, so that's the same number twice, is always equal to 0. So using this fundamental theorem of calculus, the integral from a to a of f of x, well, we're going to plug in a and then subtract plugging in a. So f of a minus f of a, that's the same thing, and that will always be equal to 0. So if those numbers are not different, if they are the same, then that integral is 0. All right, we have the same setup as before. This property says that the integral from a to b is the negative of the integral from b to a, right? So if you flip these guys, you pay for that with this negative sign. So here's where that comes from. We take the integral from a to b, right? So that's what we started with. By the fundamental theorem of calculus, we plug in b to the antiderivative and then subtract plugging in a. And now if I pull a negative sign out of that, the negative f of a, which is the second term, becomes positive, and the positive f of b, which was the first term, becomes negative. So all I did was rewrite this as a negative sign out, and then I changed the order of my subtraction. And now this inside the parentheses, f of a minus f of b, that is, again, by the fundamental theorem of calculus, the definite integral from b to a. And that negative sign hung out in the front. Right, so if you're going to change the order of a and b, you pay for that with a negative sign. For this property, we'll start with the same setup as before for f of x, and we also need a second function g of x. Then, if we're adding or subtracting little f and little g on the inside of this definite integral, we can add or subtract the definite integrals of the two functions where we take them separately. Right, so that's the same property we saw with indefinite integrals, and here's the reasoning behind that in case you're interested. So by the fundamental theorem of calculus, we're going to take what's inside here, find the antiderivative, which would be f plus or minus g. We plug b into that, and then subtract plugging in a. And then by rearranging things, I can take this f of b minus this f of a and put that here. And then I pull this plus or minus sign out, and I get g of b minus g of a, and that goes here. So that's just rearranging things. And then again, going on the other side, the other direction with the fundamental theorem of calculus, this is the definite integral from a to b of f plus or minus the definite integral from a to b of g. All right, so that's, again, the same property we saw before with indefinite integrals, that if you're adding or subtracting on the inside of that integral, you can break it up and find the integrals separately and then add or subtract them. Now let's take the same setup as before with f, and I'm going to say we're going to take an a and a b, and let c be some number in between a and b. Then the definite integral from a to b is the integral from a to c, where you stop at c, and then you add where you start at c and go to b. Right? So you're starting at a, and instead of going from a all the way to b, we're going to go from a to c, and then from c to b. And the reasoning behind that with this fundamental theorem of calculus, again, this is just the original statement of the fundamental theorem of calculus. And then I brought that f of b along and that negative f of a along. And then in between, I've just added and subtracted f of c. So that's just writing down plus 0. And then just rearranging my terms, I can take f of c minus f of a plus f of b minus f of c. And working backwards with the fundamental theorem of calculus, I get exactly what I have at the top, where it's the integral from a to c plus the integral from c to b. So we can always break up our integrals in this way. Okay, now let's evaluate some integrals, right? We're going to use all of our properties that we've been looking at and evaluate these definite integrals. So, for this guy, we've got the integral from 2 to 4 of x cubed plus 3 dx. So using our fundamental theorem of calculus, we need to find first the antiderivative of x cubed plus 3. So x cubed becomes x to the 4th divided by 4. And then plus 3 becomes plus 3x. So that is the antiderivative. And then since we're doing a definite integral from 2 to 4, we want to evaluate this function starting at 2 and ending at 4. So that's that big vertical bar, 2 at the bottom, 4 at the top. And what that means is that we're going to plug in 4 and then subtract whatever we get from plugging in 3. So plugging in 4, we get 4 to the 4 over 4 plus 3 times 4. So that's plugging in 4, and then we're going to subtract plugging in 2. So that's 2 to the 4 over 4 plus 3 times 2. All right, and then check my work here, of course, but I got so again, we want to evaluate this integral. So we have the definite integral from 0 to 3 of 2e to the 5x dx. So we know by that fundamental theorem of calculus, this is going to be equal to the antiderivative, and then we're going to evaluate it from 0 to 3. So we need the antiderivative of 2e to the 5x. So remember that 2 comes along for the ride. And the e to the 5x, when you take the antiderivative, becomes e to the 5x over 5. And then we want to evaluate that from 0 to 3. So that means we're going to plug in 3, and then whatever we get, we're going to subtract from that whatever we get by plugging in 0. So that looks like 2 times e to the 3 times 5 is 15 over 5 minus 2 times e to the 5 times 0. So that's e to the 0 over 5. And e to the 0, right? E is just some number, so any number to the 0 is just 1. So we can rewrite this as 2 times e to the 15 over 5 minus 2/5. And that is a perfectly acceptable answer. Right, so we took the antiderivative, we plugged in the top guy, and then subtract whatever we get when we plug in the bottom guy. And that's our answer. Okay, next example here. Again, the definite integral, this time from 1 to 4 of the square root of 3x minus 1 over x. So we need to find the antiderivative of the square root of 3x minus 1 over x. So the square root of 3x, how can we find the antiderivative of that? Well, it might be helpful to first rewrite this definite integral with the square root of 3x as 3x to the 1/2. Right? All of that 3x is raised to the 1/2 minus 1 over x dx. And now we have to remember that since we're multiplying on the base, multiplying in the base of that exponent means we can pull that exponent down to each. And what that really means is that we can rewrite this as the integral from 1 to 4 of 3 to the 1/2, which is just the square root of 3, some number, times x to the 1/2 minus 1 over x dx. All right, so however we need to rewrite that so that we can see how to use this rule of the x to the n to take that antiderivative. That's going to be our first step. And now let's take that antiderivative. Well, the square root of 3, 3 to the 1/2, however you want to write that, that's just a number. It comes along for the ride. Then x to the 1/2, when we take the antiderivative, we get x to the, and then we raise the exponent by 1. So 1/2 plus 1 is 3/2. And divide by that new exponent that is 3/2. And then we're going to subtract the antiderivative of 1 over x, which is the natural log of the absolute value of x. And this whole thing, which is the antiderivative of the stuff on the inside, is what we want to evaluate starting at 1 and ending at 4. Plug in 4, you'll get 2 times. It's 8. Divided by 3/2. 16/3. So what do we get when we plug in 4? Let's do that first. Well, we get the square root of 3 times 4 to the 3/2 over 3/2 minus the natural log, and then the absolute value of 4 is just 4 because 4 is a positive number. So that's what we get by plugging in 4. And then we will subtract whatever we get when we plug in 1, and that's going to be the square root of 3 times 1 to the 3/2 over 3/2 minus, and then what is the natural log of 1? Well, that's just 0, so you can write this as the natural log of 1, or you can write minus 0, or you can just write nothing, right, and let all of that go away, because minus 0 doesn't change the answer. And I'm okay if you guys stop right here and don't simplify this. So now let's move on to looking at these definite integrals and interpreting them as an accumulation. All right, so remember that this definite integral, this is our fundamental theorem of calculus. And here this is capital F prime is little f. All right, so the integral, the definite integral from a to b of f of x, little f, is f of b minus f of a. But it also represents the amount accumulated by capital F from a to b. And all that really means is the amount accumulated by f, how much f gains as x goes from a to b, is just represented by this difference here, f of b minus f of a. But this allows us to interpret this definite integral as an accumulation of the antiderivative f of x. So let's look at an example of that. If a prime represents the rate, right? A prime is a rate at which money in an account is changing, then the antiderivative a would represent the amount of money in the account, right? So the rate at which the amount of money in an account is changing, if that's the derivative, then when you take the integral, the antiderivative, you end up with just the amount, the thing that is changing, right? The amount. So a of t here would be the amount after t months. And so that definite integral of a prime, this is the fundamental theorem of calculus, would be a of b minus a of a. And that is the accumulation of the amount from t equals a to t equals b. Another way to say that is that's the amount of money that is hopefully gained, since it's money, right? So you'd think that's the amount of money that is gained by that account, or the amount of money put in, or maybe if you lose money, that's the amount of money lost in that account from month A up to month B. And we can represent that with this definite integral of a prime. So that's the amount of money accumulated from month A to month B. Let's look at another example of that. So here's another example of that. It says if P prime represents the rate at which a population is changing, so P prime is the rate at which the population is changing, then that tells you that P, the antiderivative, is going to be the actual population, right? If P prime is the rate at which the population is changing, then P is the population, and the rate at which it is changing, if you took the derivative, would be P prime. So if we want to interpret the definite integral from a to b of P prime, that's going to give us, we know by the fundamental theorem of calculus, P of b minus P of a. And that is the amounts that the population changes from time A to time B. And that's our interpretation, right? You have to figure out what is the antiderivative, what does it represent, and then it's going to be how that is changing from A to B. So in this case, we're talking about the rate at which the population is changing, that's P prime. So the antiderivative is the actual population. So this definite integral gives you the accumulation of that population. That is to say, it gives you how the population changes from time A to time B. Because it's a marginal cost, right? We've been talking about marginal cost for a while. So if C prime is the marginal cost, then C of x is going to give you the actual cost of making X things or producing X items. So again, if we are given the marginal cost, then the antiderivative C would be the actual cost. So if we want to interpret the definite integral from a to b of C prime of x, again, by the fundamental theorem of calculus, that's C of b minus C of a, and that's going to give us how the cost has changed from when we made A things to when we made B things. It's going to give us the difference in cost from starting out at making A things and going all the way up to making B things. Another way to say it is that's the accumulation of your cost from when X was A to when X was B. Okay, so let's look at another example here. It says Big John's jerky stand finds that the marginal revenue in dollars from the sale of X pounds of jerky per week is given by R prime of X is 150 plus 2X. It says if Big John makes 300 pounds of jerky per week, what is his revenue? All right, so we are trying to find the revenue when 300 pounds of jerky are made per week. So if we're given R prime, we know that the indefinite integral, of R prime of X. So we're saying what's the antiderivative of R prime of X? Well, that's going to be the revenue. And in this case, we have to do a plus C because it is an indefinite integral. And what I didn't say here, but I'm going to assume, is that if I make no jerky every week, aka X equals 0, then the revenue, well, if I didn't make anything, I didn't sell anything, so I shouldn't have brought in any money. So I'm assuming here that R of 0 equals 0, and I'm going to use that point to figure out what C is equal to. So first, let's find this antiderivative where we plug in R prime is 150 plus 2X dx. So what is the antiderivative? Well, we get 150 times X, and the antiderivative of 2X is a plus 2, you could write 2X squared over 2, but that's the same as just X squared. And again, you could take the derivative of the right side and double check that you got what was inside this integral on the left side. And here's when we're going to add the plus C. And now using this point, we can see that if we plug in 0, that just gives us C. So that gives you C equals 0 because 0 plus 0, that's plugging in X for the first two terms, plus C. And then we set that equal to the 0 from the right side of this equation. And that just gives us, well, C equals 0 because 0 plus 0 goes away. So that means that our revenue function, R of X, the antiderivative of the marginal revenue, is 150X plus X squared. So I know if I make X pounds of jerky every week, then this is going to spit out my weekly revenue. So specifically here, I want to know what is that revenue at the 300 pound mark. So that question is answered by plugging in 300 for X. So we want R of 300. And you can double check my work here, but I got 135,000, and that'll be in dollars. So my weekly revenue, if I make 300 pounds of jerky a week, will be $135,000. All right, now let's look at this second question here. And that says, by how much will the revenue increase if Big John increases production, so from 300 to 500 pounds per week? And so the way we figure that out is using a definite integral. We're looking for how the revenue increases from 300 to 500. So if we take the integral from 300 to 500 of not the revenue but the marginal revenue, that's going to give us how this revenue accumulates from 300 to 500, or how it increases from 300 to 500. Right, so remember, we already took that antiderivative and we got 150x plus x squared. And since this is a definite integral, we want to evaluate that from 500 to 300. So first, let's plug in 500. When you plug in 500, what do you get? integrals. So there's your homework, and there's Sully. Make sure you guys come to class with any questions that you have. Try the homework and attempt it maybe, and we will go over that next time.